All right, so if you all can see these, I'll just go very briefly through what we discussed here. We talked about science priorities for sampling, and although we're going to the South Pole really because of the volatiles, investigating polar volatiles should not necessarily dominate our sampling. We've got a range of other things to do, geologic context, these big questions about trying to get sample material from South Pole Lake and Basin, from the feldspathic crust, volcanic rock materials in regolith, and even looking at space weathering. These are all important and key science goals. And so it was actually suggested that we come up with a science traceability matrix. That's a good idea, a lot of work. Maybe we'll try to do that. But in terms of investigating polar volatiles and organic materials, there will be some reconnaissance aspect to this. And so with subsequent Artemis missions, as we learn things, sampling priorities may shift. In terms of field sort of analytical approaches and tools, we heard today about Apollo tools. There are things that can be done to sort of improve these, for instance, with the rake tool having adjustable tines, cores and drive tubes having the ability to do this in an automated fashion is absolutely essential. Whether or not we have a roving vehicle, we need to be able to get samples from diverse locations, so we need some kind of mobility or traverse planning. Handheld instruments, certainly, but the point is made that an instrument in the hand displaces something else, and so we have to be careful with our use of any kinds of additional things that astronauts have to carry. Having these things on a roving vehicle would be useful. Imagers, rover-mounted imagers, hand lens capability with some kind of device would be nice. Heads-up display for astronauts, this just seems like a no-brainer. But at the same time, mechanisms to avoid sensory overload, documentation is key. Robotic sample collection might be able to do some of the things that we would like to do, and certainly might help if we have a robotic sample return mission with sample down mass, which is something that we're concerned about. Samples for ISRU studies, we have to figure out what's the right percentage. And again, this may be something that as we learn initially we'll better understand, but what mass and volume, what percentage of the total sample should be for ISRU. It was suggested, and this is a great suggestion, that regolith samples, big regolith samples, are useful for ISRU studies, but they also contain rock fragments, and we could potentially high grade the rock fragments and leave the fines for the ISRU because that's what is needed for ISRU anyway. We need to, all of these things we need to understand. These are sort of engineering purposes. We want to use regolith for construction. What are the physical properties? Are the polar samples, the polar regolith materials different from low latitude? Collecting samples, again, the very fine, the ultrafine materials to see if polar samples are different from lower latitude samples. And then, many of these these are sort of mass intensive. We can do a lot for science with smaller and smaller samples, but many of these kinds of engineering purposes need mass intensive samples. And again, we recognize that with subsequent Artemis missions, some of the sampling priorities may change. Then we just list things here. We didn't have too much discussion of this, but the contingency sample is very, very important. For science, we should consider a drive tube for contingency. And again, large regolith samples are good for contingency because they'll serve multiple purposes, science and engineering. Large rocks are needed so that we can really untangle some of the complexities associated with impact basin ejected material and really work out the science relationships. Bulk regolith at multiple locations, cores and drive tubes, especially if we determine that we can sample ice-bearing regolith, then these become very, very important samples. But also automating that so that astronauts are not having to expend huge amounts of energy and time to do that. Rake and sieve samples, again, are very important. Rake samples produced some of the most important samples we have in the Apollo collection. And surface regolith, the kind of material that's right at the surface, the upper few millimeters even, are very important for our understanding of space weathering and how to tie what we're looking at in the samples with what we look at with remote sensing. And then we had a lot of discussion, there was a lot of discussion earlier about the preservation of ices. I don't think I'll rehash all of that, but clearly there seems to be a concern among those who were discussing this, that sealing, getting good capability to seal samples on the surface and not worry as much about maintaining thermal control. You know, for example, you can have a container that can siphon off volatiles if they are liberated with heating or movement or what have you during sample return. Comet surface sample return has addressed this, and so we can certainly look to that technology effort to solve this problem. Shouldn't be a problem. And then just some issues that we want to address. Criteria that, you know, we want to understand the criteria that would be used to determine that the South Pole really is where we want to set a permanent base. How do we address that with samples? ISRU, we need to understand if the South Polar region and its regolith are really the right places to do ISRU. Surviving the night, we recognize that near constant illumination is an issue, and that's one of the reasons we want to be near the South Pole. And then again, concerns about sample collection and the sample down mass for return to Earth. Really want to emphasize the scientific reasons for maximizing this. Okay, so that's primarily what we discussed. And Julie, why don't I turn this back over to you to talk about curation issues and finish us off.
Okay, let's see if I can actually share my screen.
Let's see if I can unshare. Or maybe you can just take the ball from me.
All right, can you guys see my my slide that says breakout number 2 curation on there?
Yes.
Excellent. Okay, so I don't have real-time notes the way Brad does, so I'm just going to kind of run through our topics of discussion and give a very brief, super brief overview since we're getting close to the top of the hour. So the first thing we talked about, let me go through these. The first thing we talked about was contamination and the contamination concerns in terms of sample collection, containment and transport, and curation. And so we talked a lot about this kind of overlaps with the next one, which is material selection, but talking about witness materials and the importance of documenting the different types of contamination and the different spatial distribution of contamination throughout the mission and within the curation labs. And so having witness plates and witness coupons deployed within the cabin with the crew, potentially as part of the tools, in the sample containers, and definitely in the curation labs where the samples will be manipulated, is something that is critical. And depending on what we're going to measure on those witness plates and coupons, we may need varying surface areas, and we may need varying types of materials that the coupons are actually made of. And so we talked about different types of contamination. There's obviously, you know, particulate contamination and very fine metal fragments, for example, from tools and the sample containers themselves. In addition, we talked about organic contamination and volatile contamination and how the tracking and preservation of the witness materials for that may be very different than what we do for the more solid particulates. And so that was something that we have an action to go and look at previous witness coupons and witness plates that were used for previous robotic sample return missions, so that we can understand the shelf life of those materials and the effectiveness of those materials in preserving the contaminants that we're wanting to track and we're wanting to mitigate in the samples. So we also talked about material selection. This is a very big issue because we are very mass limited for Artemis, and so we are revisiting the material selection. Obviously, the Apollo materials were by and large very good for sample collection and sample preservation, but especially in terms of stainless steel, it's very heavy. And so there are some more modern materials that are lighter and just as strong, if not stronger, that could be used. And so we talked about the potential benefits and drawbacks of those, and how the tools, especially, and also the containers, could be designed to maybe incorporate some of these lighter materials without presenting a contamination risk to the samples. And that weight savings that we could get from, especially the sample containers, since that's what's going to be coming back to Earth, that weight savings will directly translate into a higher sample mass that we'll be able to collect and return to Earth. So it's something that's very important for us to investigate. And so we talked about some ways around that in terms of having lighter materials inside of tools and heavier but contamination acceptable materials on the outside of those, and that might be a challenge when we go into PSRs where you may have differential thermal behaviors of those materials, and so we would have to incorporate that into the designs, as well as considering that these things are going to get probably more brittle at cryogenic temperatures, and what kind of contamination and particulate contamination in particular that might pose for the samples. We also talked about the curation of volatiles, and we also talked about the vacuum sealing question, and I think we came to the same general consensus that we need a vacuum sealed container. That should be the top priority. However, how we make that seal and how we make that seal out of chemically compatible materials with the volatiles that are going to be in the container is probably the biggest hurdle we have right now in terms of collecting and returning volatiles. And so we talked about having potential coatings on the inside of the volatiles sensitive sample containers, and how those coatings may prevent reactions with the volatiles, but they may also preclude some of the geochemical analyses that we want to be done on those samples. And so we may actually have to collect a suite of samples where we have one set that's for volatiles that has the volatile resistant coatings on the inside, and those are just for volatiles analysis and not for geochemistry. And then we collect another set of samples from inside PSRs where we actually deliberately allow those to heat up and the volatiles get released from those. And that way we can use a stainless steel, for example, sample container to store those, and that would allow us to do the geochemical analyses on samples from PSRs. So we have some potential solutions there. It was great because we had some of the sample tools engineers there as well, and so they were able to talk about some of their concerns and some of their thoughts in terms of collecting samples from PSRs and material selection. And so we had a really great discussion, and I think one of the things that came out of this is that the science community needs to learn more about what the engineers are doing, not just for the tools and containers, but also for the vehicles, the spacecraft themselves, the propellants that are going to be used, and the spacesuits, so they can understand what the potential sources of contamination are and how we can mitigate those when we collect and return the samples. We also talked about big picture science for volatiles. I'm not going to go through this, but this is just kind of, I put this up to help facilitate the conversation. And we talked about the science measurements that folks would want to make on the samples, and what could end up derailing efforts for sample collection on the surface and in transit back to Earth, and also in the lab. And so there are some specific constraints in terms of how we clean, for example, the sample handling tools. and how those, we need to maintain those, and we need to make sure that the sample tools and containers also have the same type of cleanliness rigor that we will have for the curatorial tools on the ground, so that we limit contamination of the samples. And I think we're pretty much at 4, or I guess 5 o'clock for those on the East Coast. So, we filled the time and then some, and I think we had a really great discussion about curation. So I'll go ahead and stop sharing my slides, and I'll go ahead and close us out for the day, because I know we're at the end of our time. I want to, first of all, thank all of the speakers for the day. So hopefully there's a lot of you still online. We really appreciate you guys taking the time to talk to us today and present your slides. I know this was a relatively short turnaround in terms of when we asked you to present and when we asked you to submit the slides. And so we really appreciate everyone pulling together to make this happen. I also want to thank our next gen facilitators and documentarians, Brian Konecki and Claire McLeod, for helping to just take notes throughout the day and help to lead some of the different talks and keep time for us. And we really appreciate that volunteer effort that they put in. I also want to thank Christina Gibbs and Deborah Needham and Kelsey Young, just in general, for helping to facilitate the workshop, but also for being the slide advancers for the day, because that went really well, and I'm really glad we had all of you to help with that. So we really appreciate it, and especially to Kelsey for organizing the workshops. And this is not the last one, so there will be more. And so thanks to her and the folks at headquarters who are facilitating this and participating, I think this is really going to help us for Artemis quite a bit. And I also want to thank the folks at LPI and Survey, especially Ricky Guest, who has been doing all of our WebEx and Teams organization today, and having that timer on the screen was super helpful. So thank you, Ricky, for helping us throughout the day and making sure we had a smooth workshop today. So with that, that's pretty much all we had. So thanks everyone. We will have a recording of all the presentations that's going to go up on the website. In addition, we are going to have final reports that are going to come out. The one for the previous workshop just got posted, I think, a few days ago, maybe a week ago. And so, within the next few weeks, we'll have similar products for this workshop, and we are going to ask for community inputs on that. So, please keep an eye out for that, because we want to continue the discussions with everyone. So thank you very much. And Brad or Sarah or Kelsey, if you have anything you want to say, please chime in.
Yeah, I just want to add a thanks, what Julie said, thanks to all of you who participated, and thanks to all that she mentioned, and thanks also to you, Julie, who she did really a lion's share of the work of communicating with folks about presentations and did an awful lot of things. I'm very grateful for that. And folks, stay engaged. This is our chance to really make our voices heard and have some input to the Artemis program, and it's essential that we continue to do so. So thanks again.
And thank you, Brad. I forgot to thank my co-chair. So thank you for helping to organize everything today as well. I appreciate it. All right. Well, I think we're done for the day. Thanks, everyone. And we'll see you next time. Have a great evening.